Today we're going to be talking about eigenvalues and how we find them. So what is an eigenvalue? If we have a vector, so we'll draw out some 2D space here, or 3D, doesn't really matter. If we have a vector like this, when we perform some sort of transformation on this vector, it's going to be stretched, or it's going to be rotated, or something's going to happen to this vector. And so when we do this transformation to all the vectors in a space, so every single arrow in here, they're all going to be stretched and rotated in their own special way. But some vectors, a special thing happens to them. So what happens is these vectors, instead of being rotated, they're only stretched. So for example, this vector here, the red one, would end up here, or the red one would end up here. But you notice that it's only ever a scalar multiple of itself. So this blue vector is 2 times the red one, and this yellow one over here is just -1 times the red one. But you notice that there's no rotation. So this green value here, green vector, isn't what we'd call an eigenvector. But the blue and the yellow ones are eigenvectors because they stayed in the same line here. They remain scalar multiples of the original vector. And so the eigenvalue is the value that we assign that tells us how much it gets stretched. So for this blue vector, we denote eigenvalue with lambda. We'd say that the eigenvalue is 2 because it's really just 2 times the red one. And for this yellow vector right here, we'd say that the eigenvalue is -1 because it's really just -1 times this original red vector here. And so if we're given a transformation matrix, how do we find out what these eigenvalues are going to be? And we're going to go through an example here in 1 minute, but the easiest way to do it is if you have your matrix, you get some values A, B, C, just like this. If we take the determinant of this matrix A minus lambda on the diagonals, so like this, when we take the determinant of this new matrix here, the values of lambda that make this determinant 0 are going to be our eigenvalues. And so the way that we write this notationally is it's the determinant of A minus lambda I, where I is the identity matrix, and that's just a matrix with 1s along the diagonal. And so what happens when we multiply this by lambda is that we really just end up with lambda along the diagonal, which is where you get A minus lambda on the diagonal. So let's work through a quick example. Say we have, sorry about that, I'm jumping ahead a little. Say we have this transformation matrix here. We'll call it T actually. So say this matrix transforms a vector, and we want to find out what the eigenvalues are. So the vectors that just get stretched, how much do they get stretched? So what we want to do is we want to find the determinant of we'll call this A minus lambda I. And so what that means is that we want to find the determinant when we subtract lambda from the diagonals. So we're now looking for the determinant of this matrix here. And so the easiest way to find the determinant is we're going to do cofactor expansion. So you can pick any column. It's helpful that there's all these zeros here, so we can kind of do whatever order we'd like. But I think the easiest way is to start with this middle column because there's a whole lot of zeros. So for cofactor expansion, the first thing we do is the determinant of this big matrix is actually the same as a sort of algorithm we'll use to find the determinant of a bunch of smaller, easier to calculate matrix. So the first one we do is we see that this is 1, 2. This right here, we're going to pick this column, the second column. And so we start with the first row and the second column. So we're going to do -1 to the power of row plus column. So 2 plus 1 times whatever value is here times 0 times the determinant of the matrix when we ignore this 0. So we cross out the row that it's in, and we cross out the column that it's in, and what this leaves us with is the determinant of 0, 0, -1, 5 minus lambda. Now this is really helpful because we can speed up all our calculations. Because we're multiplying by 0, we already know this is immediately 0. So we can kind of ignore this when we get to our next step. The next step in cofactor expansion is to go to this next row here. So we're looking at this value, 4 minus lambda. So this is the second row and the second column. So we're doing -1 to the power of 2 plus 2 times this value right here, so times 4 minus lambda times the determinant of whatever's left. So if we cross this out, we get the determinant of 5 minus lambda, -1, -1, and 5 minus lambda. And then again, this last step here, we're left with another 0. So we could go through the work again, but we know we're just going to be multiplying by 0, so it's going to end up being 0. So now that we know this is 0, we can kind of rewrite our whole expression. -1 to an even power is just 1, so we can ignore it. And so we're left with the determinant of a minus lambda I is equal to 4 minus lambda times the determinant of 5 minus lambda, -1, -1, and 5 minus lambda. And so to calculate the determinant of a 2 by 2 matrix, all we do is we multiply this diagonal, and we multiply this diagonal, and we subtract the second multiplication from the first one. So we're going to end up with 4 minus lambda times 5 minus lambda times 5 minus lambda. We can write as 5 minus lambda squared minus -1 times -1. And so what this gives us is 4 minus lambda times 5 minus lambda squared minus 1. And so what we could do is expand this all out, multiply these all out, and then reduce it again and factorize it to get our roots. Or an easier way to do this is to notice that this is a squared number and this is a squared number, and so we can use difference of squares. So a squared minus b squared is the same thing as a plus b times a minus b. So we'll rewrite this, 4 minus lambda times, we got 5 minus lambda minus 1 times 5 minus lambda plus 1. And so what this leaves us with is 4 minus lambda times 5 minus 1 is 4, so 4 minus lambda times 5 plus 1 is 6, 6 minus lambda. And so what we call this is the characteristic polynomial of the matrix. And to find our eigenvalues, all we have to do is find the roots of this equation. So the root of this, we can see here that this, when lambda is 4, gives us 0, lambda is 4 gives us 0, and lambda is 6 gives us 0. So we'd say that the eigenvalues are 4 and 6. And so what's important to note now that we got 4 and 6, because 4 shows up twice, we'll say that the algebraic multiplicity of 4 is 2, and because 6 only shows up once, the algebraic multiplicity of 6 is 1. But that's just a little trivia that you might be asked during a test. So there you have it. That's how you find the eigenvalues of a given transformation matrix.